Dear ladies and gentlemen, my name is Bernhard Reitinger. I work for the Research Center for Non-Destructive Testing Technology called RECENT in Linz in Austria. And today I would like to show you a little bit what we are working on laser ultrasound, especially on a robotized LaserUltrasonic NDT system for the inspection of composite parts. So what is our motivation for doing research into this area? So if we look on composite parts used for civil aircrafts, then we can have a look, for example, here on Boeing. So in the late 60s, when the 747 was introduced, we almost had no composite parts in it. This was composed mainly by aluminum and steel parts. But then if we go a little bit later, like the 757 or the 777, here in the mid of the 90s, we have around 12.5% of the structural weight composed by composite parts. And even if we go to the 787, then we have half the structural weight composed by composite parts. Also, if we look at the Airbus A350 XYB, we have a little bit more than half of the structural weight composed of composite parts. And this, of course, also means that special testing technology and special effort needs to be done to test all these structures. Also, if we look on modern and future aircrafts like drones for civil person transportation, like the Volocopter, which I guess is built in Germany, or the EHang, which is now discussed a lot, how it can be introduced in different countries and also used for civil air transportation. These products are composed by a much higher percentage of composite parts. Furthermore, if we look on modern way of producing composite parts. So traditionally, like wings were produced by different components, like the outer hull. Here on the inside we have these different parts, and we have the lower hull. Typically they were at first produced each by each and then tested, and then they were glued together and then tested again. So future production has a different way of producing these parts in more or less in an additive way by a one-shot production, which means that the part is composed by just one part, which also means that the inner parts are not anymore able to be tested from the outside. So we need flexible ways of non-destructive testing technologies which can go inside of a plane, of a wing, and to test these ribs. So what NDT is able to solve these challenges? Well, of course, there exist a lot of non-destructive technologies already used in the aircraft industry and also used for composite parts. But traditionally, ultrasonic NDT testing is a good way to go for automated bulk material testing, which means that we really want to know if there are flaws inside of the material and not just only looking on the outside for cracks. So let's have a look on the state of the art of testing composite parts by water-coupled ultrasonic testing technologies. Like here on the left we have the tower systems, which are mainly based by single element ultrasonic squirter systems, like the ones here. So they were built for very large structures and, well, of course, quite inflexible when the parts got larger or got a different size. So yeah, since I guess around 5 years, we also see the advent of robots coming into non-destructive testing. Here we see a robot which is especially adapted to non-destructive testing, so it has a higher active accuracy, which means also when the trajectory is much smoother and much accurate than traditional ones. We also see that this one uses phased array, so with phased array we also come to much higher square meters per hour of testing speed. Then of course we have also air-coupled ultrasonic systems. Like on the right hand side we see the RECENDT system, which tests, I guess this is a rocket from the Ariane, and they are testing this in through transmission mode. So we have a very large robot on the outside, on the inside also some fixed structure. And on the left hand side we see an air coupled system which is in pitch catch configuration, so it measures just from one side and therefore it can test different structures. And at last we have the laser-based ultrasonic systems, like the one on the left-hand side, which was originally built by Lockheed Martin and then sold to PAR Systems, and on the right-hand side the iPhoton system, which is now, I think, sold by Technatom, or maybe both by Technatom, I don't know really. So both of these systems are more or less built by the same persons or developed by the same persons, so the core system is much more or less the same. Generation is done by a CO2 laser and detection by a neodymium YAG laser. The CO2 laser has a few drawbacks, like here on the backside we see it's quite heavy, quite large, and it's also not able to be fiberized. So therefore we see this big tube system going around. So if we compare these ultrasonic testing technologies, on the left-hand side we have the water-coupled ultrasound, then we have the air-coupled ultrasound, laser-based ultrasound. So although the water-coupled ultrasound is quite fast, we have the benefits of the air-coupled ultrasound, laser-based ultrasonic system, that they don't need a coupling agent, which is quite beneficial. And also for the laser-based system, this typically is used in pulse echo regime, which means we get depth information. Also, if you look at the bandwidth of the acoustic wave, typically for air coupled we have around 50 kHz to 500 kHz, which is quite low in comparison to laser based, which is around 500 kHz to 20 MHz. And also, if we think back to the modern way of producing composite parts, miniaturized, very small miniaturized probes were already shown, which were used for photoacoustic imaging and which is quite similar to laser ultrasonic systems. So therefore we are doing research and we went for laser ultrasonics. So what is laser ultrasound about? Laser ultrasound is more or less, well, the acoustics inside of the material is the same, but generation and detection is different. So we have an excitation laser which focuses a nanosecond laser high energy pulse to the surface. Therefore the surface is heated, we have some volume expansion, and because of the volume expansion we have a broadband ultrasonic wave is generated. And on the other side we have a second laser which shines on the same spot, or maybe a little bit a different spot, and records the movement of the surface, which is caused by the ultrasonic wave which comes back to the surface. So this is a typical signal where we have, here we see the surface bang, which is caused by this volume expansion, and the first echo, this is the first reflection from the defect. So we have the benefits of being contactless and also high bandwidth, which is, of course, which depends on the material itself. So for composites we go around 20 MHz, for steel it's a little bit higher, and we can also go to up to 700 MHz in our laboratory, of course with a different excitation laser. So our motivation is development of a laser-based non-destructive testing system with a much reduced footprint in comparison to the CO2-based lasers, reduced costs also in comparison to these systems, enhanced flexibility, fully automated, fast scanning, and also, and this was very important for us, not complicated part handling like using fixtures. So we started in, I guess, around 2016-17, the Accurate project, which is part of the Clean Sky 2 framework. The project had a funding of around 2 million, lasts 30 months, and is now extended up to 2021 for the installation at the topic leader's place. The consortium of the Accurate project consists of TWI, who is leading the project. And well, let's have a look on the different partners. So we have KUKA, who is dealing with all the robots. We have TWI, who is doing the data acquisition and robot path planning. We have Innolas Laser, who develops and manufactures the lasers. And we have RECENT, who brings in all the laser ultrasonic know-how into the project and developed the laser ultrasonic probe system for mounting the robot and the two-wave mixing interferometer. The aim of the project is to develop a laser ultrasonic testing system for non-destructive testing inspection. Well, here on the right hand side you see this large aircraft structure and also the robot, which is mounted on such a transversal stage. And here we see some different types of structures which need to be tested within this project. So let's have a look at the parts which we built. So at first we have the generation laser, and in contrast to the other laser ultrasonic systems which I showed you at the beginning, this one is based on a diode pump neodymium YAG laser. So it's much smaller, has a much smaller footprint compared to the CO2 laser, costs also much less and is much better to work with. And also the greatest benefit of this one is it's it can be fiberized. So bringing it to the end of a robot effector is much easier. Then we also have the detection laser, and the detection laser is built out of a low noise cedar, which is then amplified also by a diode pump neodymium YAG laser. Then we built the optical probe, which is further mounted onto the robot. We started this by doing CMAX optical ray tracing simulations, then building this prototype where here the generation laser goes and is coupled by a dichroic mirror to the detection system. Here we see a spot of the generation, or an image of the generation spot, and we also built the two-wave mixing interferometer. So if we look at the robotic system, it's composed of a KUKA KR30 robot manipulator, which is standing on a linear track which can move 2.7 meter. And also we were thinking about all safety issues because we are using class 4 lasers. So we also integrated interlock door locking systems and all the different access systems. Here you can see the Accurate system in, well, let's try to start this one in action. So the robot moves to the sample. I think in the next we will see the probe. Yeah. So the robot moves along the surface. Before that, a trajectory was programmed into the system, and therefore the system scans the whole surface. So we can see here the first result of the plate. We have different, this is the time of flight scan. We have different artificial defects brought into the sample, and here is another sample where we have some ribs, some different types of integrated structures into the samples. So here is a first result. This is of the Clean Sky 2 panel. Here we have structure inside. Here we have different flaws inside, artificial defects, and also here we have a different way of working with the data by a histogram filtering function. Again, here we have another panel with stringers and ribs on the back side, and if we look on the data, we can again see the time of flight, the thickness of the material, and also some other parts included in here. So, but then we wanted to see a little bit more how the accuracy and how the laser ultrasonic results are in comparison to other technologies. So we built a composite sample with artificial defects like Teflon foils, and this is the first result. Here we see this is the geometry of the parts inside, and this is the time of flight image of the laser ultrasonic results. So here in green we have the some echoes at around 2 millimeters, and here in blue we have at a different level. So this is the C-scan slice, and we see that we can image these defects quite nicely. This is the backwall echo where all the defects typically can be seen. So if we compare this to thermography, here on the left hand side again we have the laser ultrasonic testing results, and on the right hand side we have a reflection mode, and this is by diffusion time. So here we have reflection and transmission, and if we look on the transmission images, this is illuminated from the back side and this is from the front side. We can see almost all details, almost all of the internal parts. If we look on the reflection mode, well, we can see that deeper buried defects are not really that good image. Also, furthermore, if we look on phase contrast images, like the one from the transmission mode, all the different flaws are much better visible and can be clearly seen. If we compare the laser ultrasonic results with X-ray tomography, here on the top hand side we have a slice of the image, also at 2 millimeters, and we see much better, of course, the same defects at the same locations. Of course, we also see the different defects here, and of course, well, this is the gold standard in non-destructive testing technology for composite parts, for small composite parts. So if we compare the results in a small discussion for laser ultrasound, well, for 2 millimeter depth, the C-scan perfectly matches with the X-ray tomography. We have a scan time of around 20 minutes. X-ray tomography, on the other side, of course, has the best resolution and contrast. Well, it's the gold standard in non-destructive testing technology, although one has to take into account that the voxel size typically is depending on the size of the specimen inspected. So if we are going to inspect very large specimens, voxel size can be larger than the depth or thickness of delamination, and therefore delaminations could be challenging to detect. On the other side, we have thermography. All defects were found, but only in transmission configuration. So the depth limit is around equal to the defect diameter. Whereas thermography is, of course, the fastest method, with 3 minutes compared to X-ray tomography around 125 minutes. So laser ultrasound is somewhere in the middle. So next step for us was to implement a laboratory robotic system which is based on a universal robot and also a 100 Hz system. So on the left side we have here our Techno system. We also have here an inner last generation laser which is fiber coupled, and the universal robot, where, well, at the beginning a lot of guys told us that the universal robot can't be used for this application, but it turned out to be quite good. So This is about the development of our robotic loose system and all the path planning. So we implemented a software where we can see the robot virtually and also real. So if we move the robot in the program, we see the virtual robot is moving and also the real robot is moving. And here, this is now the interesting part. Well, we didn't want to work with CAD files. We just wanted to put our sample at some place, scan it. This is now done here, and then do the path planning on this scanned surface. So we scanned the surface. Here we created a mesh, and in the next step, the mesh is placed directly onto the path in our real world, and we can do the path planning directly on this and do the testing directly there. So which should start right now. So this is the first point, this is the second point. We get all the different normals to the surface, and then the robot moves and scans the surface. So as next, we tested this on the real world composite part, which is put here. We already scanned the part and programmed a trajectory. We are controlling the robot with 10 Hertz. So at 10 Hertz rate, we give him all the next normal to the surface and distance where he should go. So you can see we scan the whole surface. Scanning distance or stepping size was around 1 millimeter. And this is because of the repetition rate of the generation and detection laser systems by 100 Hertz and the speed of the robot having 10 centimeters per second. So next we come to some results. So here on top we see time of flight image where we see the thickness is varying. Here it's much thinner, here it's thicker, and here we have these beams going away. Here we also have some logos which we put into the backside of our samples, and here we can also see some inclusions. We also had a look on the path deviation of the universal robot, and with around ±2 millimeter, it's perfect for our laser ultrasonic system. So we are quite happy. And in future, we want to control it in real time to also lower this deviation to smaller points. So this was my presentation. Thanks a lot, and I am now open to some questions.